and thanks for this opportunity to speak about this project that we've had and which is soon coming to an end. I'm from Sintef, and I've been working with two colleagues, Erling Devold and Bjørn Magnus, on this development of the real-time shrimp statistics. And it's a joint research project with Scantrol Deep Vision and Nordnes. And of course, I have to acknowledge FHF for the funding for this project. So I want to start by saying a bit about the background and context for this project, which is that shrimp trawling, especially in the Barents Sea and in the north, has been struggling with great search efforts before finding dense, profitable shrimp aggregations. Now, this effort leads to low catch efficiency and struggling with profitability. And it would be really good to have some real-time information about what you're catching instead of having to sort of trawl a bit blindly and only getting to know what you catch after you haul it on board. And it doesn't help that we have increasing fuel prices and carbon tax. So whereas in the south, the shrimp quota is quickly harvested, in the north there has been unharvested potential in later years. And here I have taken a graphic from this IMR report where we see where the catches are made in quite concentrated areas in 2025. Whereas we see that the shrimp biomass, at least the models that we have for them, is quite widespread. And so along with increasing potential for export to China, for example, increased a lot last year, there's a lot of unharvested potential that might be interesting this year and in years to come. And this makes it all the more important to have to develop technology that improves the efficiency in the fishery. So that's why we've been working with the CamSounder, which you see here, an example of. So this is a camera system that's sewn, here it's sewn into the trawl net. There are different setups that we used in this project. In terms of hardware and components, the system itself consists of a stereo camera where you have, we've used both color on both channels, but also experimenting with grayscale on the left channel, because grayscale cameras have higher light sensitivity and are better able to operate in the dark seafloor environment. But we also get some value out of having a color camera, and putting both of these aside is giving us the most information possible. There's an onboard processing platform in form of the NVIDIA Jetson Orin, which is running our AI models that I'm going to discuss in a little while. And then an acoustic link, which is transmitting catch statistics in real time to the bridge on the vessel. So I want to emphasize that we're not sending images of shrimp. That's too much information for this link, but only the small information of the statistics. And this was not tested operationally in this project, but this is due to some practical challenges that we encountered. So for the physical setup, here you have one image of a setup. We actually used a freely mounted camera, which was facing a white tarp in our trawls. And one learning from this setup, we're going to see some images from it later on, is that we wanted to have a white background against which to picture the shrimp. But it turns out the tarp, of course, not being permeable, the current is led around the tarp and the shrimp is led away from the tarp. And it turns out so you don't get the images we envisioned, but it turns out it's not needed. So we can actually see the shrimp because they reflect the light quite well. So for developing our models, we collected data with Nordnes' Vollerosa here. So we did 3 trips in total, 2 trips last year in May and September, and then 1 trip this year in February. And in total, we got more than 10,000 shrimp in our images with annotations. And these image data sets are already available on request and will be uploaded on Nasjonalt Vitenarkiv. I just learned that you can publish large data sets there, actually. So we're in the process of doing that. And that's for the raw images, and the annotations will be publicly available as well, so that you can train your own shrimp detection models and bycatch detection models. So let me say a bit how we work with these large data sets, because it's very time-consuming if we wanted to manually go through and find all these 10,000s of shrimp in these images. So we use an iterative semi-supervised process, which goes as follows. We start with a seed number of annotations. This is manual work to just bootstrap the process. It's the first step in the diagram on the left there, or on the right for you. Then we train a first model on this seed annotation data set. And we use this to predict annotations for the remaining data set. And now we go through these annotations, these predictions, and we adjust and we quality control them. Most of them we have to discard, but some of them we include. And this allows us to incorporate more annotations into our data set. And we train a new model, and we continue this way until we saturate, and we've annotated the whole data set in a satisfactory manner. And then that's when the real training of the models begins. So this is a faster procedure for these large data sets than actually going through and doing everything by hand. Okay, so now let's look at some images and the data set that we've used to train these models. So here I've put two images. I don't know if you can see. I think they're dimming the lights a bit. That's good. So yeah, now you can actually see quite a bit. But this is the raw image from one of our trawls. I've duplicated the image so that everyone can see. So as you can see, the light conditions are challenging, but we can increase the contrast a bit. And that's mostly for us. The models themselves are able to see quite well here, as we'll see now in a minute. So we've trained models on these types of images, and you see a lot of shrimp here. You see fish, bycatch. You see some eel. You also see our tarp there lying in the bottom. And when we run our models on an image like this, we get a ton of detections. And so this is what's happening down in the trawl, at the seabed bottom. We see the bycatch has been selected, the eel, and we see hundreds of shrimps being detected by this algorithm. And this is the basis for the statistics that's sent to the bridge. Now, when we have these detection models, one thing is counting the number of things we've caught, but we want to size estimate as well. So that's the point of a stereo camera system. And for that, we need to do stereo matching between the two channels. So here, I've taken a simpler picture with a bit fewer detections. And here you see the left channel and the right channel, grayscale color. And you see two shrimp detections that have been matched up in this particular scenario. And that just means we take a detection in the left image and match it with a detection in the right image. Now, in this model that we were experimenting with in the middle of the project, we were associating them by finding the most likely points to associate between the two channels. This turned out to be a bit of a power-intensive approach, and we found a simpler approach that we actually implemented in the end. But the image still stands for demonstrating how it looks like. So let me say a bit about the stereo matching approach that we ended up with, which is quite simple and efficient. And that's important when you're running on battery at the seafloor bottom. So this is based on an algorithm that was actually published last year by some South Korean authors. And I'll just say briefly how the algorithm works. Once you have detections in two images, these form vertex sets of a bipartite graph, meaning you have two separate sets of vertices. And now you're going to form a graph from this by drawing a line between these two vertex sets, and you need to put a weight on this line, and the weight is computed as follows. You take a detection in the left image and a detection in the right image, and you assume that you're going to try to make them correspond. And that makes you able to transform the right detection to the left image. And now you can compute the overlap of these two detections. And it's called the IOU, intersection over union. So that's one way of measuring how good two annotations correspond. And that gives you a value between 0 and 1. And it gives you this. For the whole, you get a bipartite graph where you try to match all detections like this. And you find the maximal matching. So each image is maximally matched to the detection that overlaps the best with it when you transform it to the left side. It's called the Hungarian algorithm. It's a classical way of solving this problem. And so it's funny that my background is in mathematics, so I was very happy to formulate it in this way and then solve it in a precise way like this. Okay, so what is the result from this? So we get catch statistics where we also have size categories for the different shrimp. So we have small, medium, and large, but we can customize that because the size estimates are numbers, really. And these are wirelessly transferred to the bridge. There's also the amount of bycatch, which with no categories as of now, but we are applying for an extension based on feedback that we gotten on the system that there are certain bycatch classes that would be interesting or useful to detect separately. In particular, this lysfläckfisk was highlighted as particularly cumbersome because it has the same acoustic signature as shrimp, at least on the Modport scanners. So it would be really useful to know in real time whether you're hitting shrimp or whether you're hitting lysfläckfisk, because it happens sometimes that they find out that they're catching lysfläckfisk instead of shrimp, and that's very disappointing. So this is just a sneak peek at the statistics view. And I really invite you to join us at the stand A118, where Scantrol has set up a live demo simulation of this system. And you can speak with me and with Hege as well. I see that she's joining us here in the audience. And feel free to reach out if you have any questions about the technology and so on. The development to me or for CamSounder requires, of course, to Hege. And yeah, thank you very much. Hope to speak with you afterwards and see you on the stand.